Hello, Chem 110. This video is about multi-step dimensional analysis. So there's another video which is on the basics of dimensional analysis. And there's really nothing super new in this video. So I want to remind you of the way I like to think of dimensional analysis, which is you have a starting point, and this is, sort of what you're given. So you have 25 mils of this or 5 grams of this. And then the problem asks you to convert that to some other units. Sometimes it's a different substance than what you started out with. And this often takes the form of how many blank do you have? So that's your end point. And then in the middle, we have conversion factors. And what makes multi-step dimensional analysis different is that you have at least 2 conversion factors. And maybe you even have more, ... All right. So the approach is really the same. So I'm going to go through 2 examples, each of which highlights something specific. And then I just want to wrap up with kind of a summary of the different conversion factors we've used so far. So example 1 is how many molecules of water are there in 15.0 milliliters of water. And as is often the case, I'm going to provide a little more information here, which is the density of water at room temperature, because it changes, by the way, is 1.01 grams per milliliter. All right, so you're welcome to stop the video at any point and try this problem. And I'll go through it so you can come back and see this. Okay, so I like to start by identifying the starting point and the end point. So the starting point is the part you can imagine yourself being handed, and that's this, 15 milliliters of water. The end point is the how many blah, 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 blah. So it's this part. We want molecules of water. And I would just note here that this is different than moles. If I wanted moles, I would say how many moles. But here I'm asking you how many individual molecules. So you should already expect if I'm handing you an amount, then probably you're going to have a lot of molecules. Okay, and then let's look at the conversion factors that we have. So there's one conversion factor given in the problem. We might end up using others, but the conversion factor given is the density, and it's very helpful to rewrite this as 1.01 gram over 1 milliliter. And just as a reminder, the 1.01 grams carries the sig figs for this, which is 3 sig figs. This 1 is infinitely significant. In other words, it doesn't factor into our sig figs at the end. Okay, so that's the only conversion factor we're given. Doesn't mean the only one we're going to use. So let's go ahead and start with our starting point. So 15.0 mils of water. And I know at the end I want to end up with, hopefully leaving enough space, molecules of water. So really the only way to get from milliliters to kind of the amount of water is through the density. So I'm going to go ahead and use that conversion factor first. I want to get rid of milliliters, so I put it on the bottom, and that means I'll have 1.01 grams of water per milliliter. That will eliminate my milliliters, and now I have grams of H2O. And I want to get from grams to molecules. And the way to get from grams, which is a macroscopic thing, to molecules, which is a microscopic thing, is to go through moles. And so I need a conversion factor that will get me from grams to moles. And that is the molar mass. So the molar mass of any compound is a conversion factor. I'm going to have to calculate this one because it wasn't given, but I can do that. That will be, if you look at your periodic table, this. So I'm filling this in, and this comes out to 18.02 grams per mole of water. So 1 mole of water is 18.02 grams. You'll notice I don't always write water. When we get to switching substances, I'll have to be a little more careful. But in this case, it's water and water. Whether or not I wrote that, it's certainly true. So my grams go away. And I'm at mole, and now I need to get to molecules. Anytime you need to get from mole to individual things, you use the definition of a mole, which is Avogadro's number. We want to get rid of mole, and we want to end up with molecules. Let's all appreciate for a moment that we have an abbreviation for mole, which is 4 letters, and we don't have an abbreviation for molecules, which is 9 letters. All right. So 1 mole is Avogadro's number. I don't really have enough room. 6.022 times 10 to the 23rd molecules. And in that case, my mole will cross out. So all I need to do now is do all the numbers. And I just want to point out that calculation-wise, you can do this a couple ways. You could multiply 15 times 1.01 times 1 times 6.022 times 10 to the 23rd, and then divide by 1802. Or you can just go in order. Your calculator will do it all correctly if you just say 15 times 1.01 divided by 18.02 times 6.022 times 10 to the 23rd. And the answer I got, I should confess I only did this once, so the answer I got when I did it once was 5.06, rounding to 3 sig figs, times 10 to the 23rd molecules of H2O. All right, I want to do one more example. And this example 2 is how many mole of H, hydrogen, are there in 1.00 liters of H2O. So again, we should do starting point. We should do end point. My starting point is what I'm being handed. 1 liter of H2O. My end point is the how many, which is mole of H. And so in this case, I just want to emphasize that you are being asked to switch units from liters to mole, and you are being asked to switch substances from H2O to H. All right, so you're welcome to try this on your own and come back, or you can watch me do it. So my starting point is 1 liter of H2O. I should say, there were no other information given in the problem, so there's no other conversion factors, although since we had just done a problem on H2O, again, I want to get to moles. The only way to get from volume of a pure substance to moles or molecules is through the density. And so we use the same density we used above, which is 1.01 grams of water per milliliter. Now, we cannot cross out liters and milliliters because they are not the same thing. So I can recognize that these are from the same family. It's just a prefix problem. So I need to do something that puts milliliters on the top and liters, excuse me, on the bottom to cancel those out. And I know that 1 liter is 1,000 or 10 to the 3rd milliliters. That's, again, infinitely significant. That's a definition. So now my liters cross out and my milliliters cross out. Excuse me. All right, so now I'm at grams H2O. I did the work of molar mass last time, so I know that 1 mole of H2O is equal to 18.02 grams of H2O. So my grams cross out, and now I have mole of H2O. But I need moles of H. And so this is a conversion factor that actually was sneakily in here. Is sneakily a word? Good question. In the chemical formula. So one thing a chemical formula does is give us mole ratios. And the 2 on H tells us there are 2 moles of H for every 1 mole of H2O. So that is key piece here. And now my moles of H2O cancel out and I'm left with moles of H. And this was a case where it's important to write the substance so that I know that this is moles of H2O versus moles of H. Okay, so again, you can just go through, multiply, and divide everything. And I ended up with 1980. That was a good year. Mole of H, if you want to be very clear that you only have 3 sig figs, you could write 1.98 times 10 to the 3 mole of H. I think it's helpful right here to end with a little summary of conversion factors. And you might make a little study guide for yourself and keep adding to this as we go. So conversion factors that we have used molar mass, right? It's grams over mole of a substance. We have used the density of pure liquids. You can do the density also of pure solids. And we've used it in units of grams per milliliter. You'll find it sometimes has other units of volume besides milliliters. So what else have we used here? We've used prefix conversion factors. So for instance, something like 1 liter over 10 to the third milliliters, or 1 meter is 10 to the 9 nanometers you might have used in Chem 111. So prefixes, you sometimes have to look them up to see what they mean, but we have used those. We have used Avogadro's number. Avogadro's number is a conversion factor that gets you from mole to individual things. And it can be any individual thing. 6.02 times 10 to the 23rd things, I'll just write, in 1 mole of those things. Usually it's atoms or molecules or electrons or something very small because, in fact, there really aren't moles of big things. It's such a huge number. And then the final thing we've just done here is mole ratios within chemical formulas. And so the example up above was, for instance, 2 mole of H in 1 mole of H2O, and we've had other examples in class. And there are other conversion factors we'll use in this class, and there are out there, but this is a list of things just to think about now that are kind of in your toolbox.